So, this last week we have been talking about circular motion and energy conservation. And, we have a contest coming tomorrow. It should be roughly 50-50 between those two. The format will be the same as the last contest. There will be 10 problems, and you choose 8 to do. If you don't mind, if you pick a conceptual question, go ahead and write your answer to the conceptual question down on your upload, but you don't have to explain conceptual questions unless it says explain. Okay, so if it doesn't say explain, it's basically multiple choice or true false, and it's just all or nothing. If it says explain, you can get some partial credit based on your explanation. Even if you have the right answer but the wrong explanation, it may be only partial credit. But if you have the wrong answer, but your explanation sort of indicates certain level of understanding, you could still, get some points. But if there's not a request for explanation, just please write your answer on the upload, because if you don't do that, then I have to sort of leave your test, and then I have to go to the other test and look and see if you chose that one. And I mean, it's not a big deal, but it would save me a few minutes and help me grade your contest faster. Okay, so you should expect it to be about 50-50. We do have some problems that kind of combine conservation of energy and circular motion. So I guess I would recommend paying special attention to those, because, there's a good chance I'll put something like that on there. So examples would be like our roller coaster problem was one where we have to use conservation of energy to find the velocity, but then we also have a circle. So there's velocity appearing in our centrifugal force equation. Okay, so since you don't have any particular questions about centrifugal force or energy, I will go ahead and move forward a little. We talked about energy, and when we first introduced it, I said it's some kind of mysterious thing that nobody really knows what it is, and it changes form and it changes hands, and so it's an example of what in physics we would call a conserved quantity. And I'm going to put the whiteboard here up before I forget. So it's an example of a conserved quantity, and we have a lot of conserved quantities in physics, but this is our first one. Our second conserved quantity is the subject of the next chapter, and it ultimately comes out of Newton's second law. So I'm going to remind you what I told you was Newton's second law, and then I'm going to let you in on a little secret, which is that I lied to you. This is not actually Newton's second law. This is not what Newton said. However, we have been calling it Newton's second law, and we've been using it. So let's see what Newton's second law really is. Okay, so this is, the second law, but not really. So the real second law, this is what Newton said. He said the sum of the forces equals change in P over change in T, where this thing P is known as the momentum. So why don't we use an M for that? Because we already use mass. We use M for mass. So P represents momentum. It's a lowercase p. And the definition of momentum, it is a vector. Sorry, I know some of you are enjoying doing energy and not having vectors, but this one is a vector. And this is mass times velocity, momentum. So what Newton's second law really says is that the sum of the forces is equal to the rate of change. When you have something change in something over change in time, that is a rate of the change of that something. So this would be sum of the forces equals the rate of change of the momentum. Okay, so what exactly is the momentum? Let's start there. Momentum is the best example The best example I like for explaining exactly what momentum is to imagine a collision occurring. So you can imagine maybe in football, American football. You have, not the real football, you know, but American football. You, sorry to all you American football fans. So you have two American football players, and they're, you know, I'm just going to draw them like circles because I don't want to take the time to draw people. And they're coming at each other head on. You've got one with a mass 1 and a velocity 1, a one with a mass 2 and a velocity 2. And they're going to just have this mighty crash. And you know, the defensive player is going to tackle the offensive player. He's going to grab on and try to take him down. And so the question is, you know, which one of these guys wins the collision, in the sense that the pair of them go one way or the other. Okay? So the answer to that question is the winner doesn't mean who's in the most pain the next day. That's a totally different thing. That has to do with who loses the most kinetic energy. But the winner, in the sense that that player gets to go in the player's preferred direction, is not the one with the most mass, and it's not the one that's going the fastest, but it's the one with the most momentum. So, for example, if one player has a mass of 100 kilograms and the V1, let's call it V1 initial, is 5 meters per second, and the other one has a mass of 120 kilograms, and the V2 initial, because it's a vector, this person is going to the left, they get a negative velocity, negative 4 meters per second. Then the winner is going to be number 1. Because the product of mass times velocity, which we would call P1 initial, would be 100 times 5, or 500. And there's no special name to these units, so they're just kilograms times meters per second. Whereas momentum 2 initial would be 120 times negative 4, and that's minus 480 kilogram meters per second. And I'm only comparing the magnitudes. Obviously, 500 being a positive number is larger than any negative number. I'm not talking about that. I mean that the magnitude 500 is bigger than the magnitude 480. So these guys, if this collision occurs and they hold on to each other, then they're going to move to the right. Okay, they're going to move to the right. So let's try to understand why, if this is what Newton said, this is what everyone calls Newton's second law. All right, before I do that, are there any questions about the definition of momentum? Okay. So why do we say, you know, net force equals ma when we really have net force equals change in P over change in time? So let's work with this a little. This would be change in mass times velocity, because that's the definition of P. And then we would have then m final v final minus m initial v initial over delta t. Now, most of the time, our mass does not change. So if m final equals m initial, I'll tell you some cases where mass does change, but normally for football players, their mass is not going to change during their collision. So we could say initial mass equals final mass. Then this becomes m times v final minus v initial over delta t, and that's m times delta v over delta t. And we know that delta v over delta t is the definition of acceleration. So if the mass is not changing, then Newton's second law, the way we've been using it, is identical to the original version of Newton's second law. But if the mass is changing, what would be examples of mass changing? So when you're driving the car on a road trip, you fill up the tank with gas, and as you drive, you use the gas. So the mass of the car is slightly decreasing. Okay? Now, it's a tiny fraction of the mass of the whole car. So it doesn't really matter so much that the mass is changing because it's a tiny effect. It would be hard for us to measure the difference. But situations like that, there are situations where you burn the fuel, for example, in a rocket ship. So in a rocket ship, you've got a rocket, you burn the fuel, and the fuel is basically that part of the rocket, okay? And the payload is there. That's the part with the instrumentation and the astronauts and whatever. That, you know, this is obviously like a 1970s style of rocket. The new SpaceX rockets have reusable canisters and things. But at any rate, in this situation, the beginning mass when this tank is full and the final mass when it's empty is very, very different. And so in such a case, it would not be accurate to say net force equals ma. In fact, for a rocket in outer space, the net force, when it's far from any planet or star, basically the net force will be 0. And so it actually couldn't move if Newton's second law were really net force equals ma. But because net force actually depends on how the momentum changes, if the mass can change, something can get a push even if there's no net force on it, or seems to get a push. Okay, so that's kind of philosophically what's going on. Now, we're going to be talking about those situations in this chapter where we can't really use net force equals ma because the mass does change, or maybe we have something that breaks into 2 pieces, and so one mass becomes 2 masses, or masses join and become 1 mass, like the collision between football players. And what we're going to see is actually, rather than being a problem that we can't use net force equals ma, this is actually a bonus that we get to use the real version of Newton's second law. So let's remember, today is more of a conceptual and philosophical introduction. We're not going to really get into problem solving, today. But I want to get a good foundation so that on Monday we can really get into these problems. So first of all, we could take this Newton's second law, net force equals delta P over delta T, and we can solve it for delta P by multiplying delta T on both sides. So we get net force times delta T equals delta P. So let me rearrange it. Delta P equals net force times, actually no, I don't want to rearrange it. I'm trying to make an analogy here. So remember, this momentum, what I'm going to show you is that this is a conserved quantity. And what we have then is some quantity, the net force times delta T, being equal to the change in our conserved quantity of momentum. Now this thing on the left, it has a name. It's called the impulse. So the net impulse is equal to the change in momentum. This is known as the impulse momentum theorem. But I want to point out that this is very similar to saying net force times delta x times cosine of phi equals change in kinetic energy, which was our work energy theorem. Net force times delta T equals change in momentum. Net force times delta x equals change in kinetic energy. They're similar ideas. The key difference really being that because, delta F and delta X are both vectors, we are combining them in such a way that what we get is a scalar. But when I have net force times delta T, what I get is still a vector. Okay? So that's the key difference here. But the potential energy, the kinetic energy, 1/2 mv squared, and the momentum, mass times v, they're very similar. They both have to do with how much mass the object has. They both have to do with the velocity. So they are related concepts, but they are not identical because momentum still has a direction associated with it. Now, this impulse, to kind of go back and look at the impulse momentum theorem. In most of our problems, one of two things is going to happen. Either the delta F, the sum of the F is going to be 0, so the net force on the system is 0, or the delta T is very, very small. And because it's very small, it doesn't really matter what delta F is. When we multiply it, we get something close to 0. So most of our work is going to be spent on the special case when delta P equals 0. So that's either net force equals 0 or delta T is very small. Okay, those are the two cases. In that case, we would say momentum is conserved. Okay, so in that case, we say momentum is conserved in the same way as when there's no work on a system, we say its energy is conserved. If there's no impulse, momentum is conserved. If you want to change the momentum of a system, then you have to have an impulse. So what exactly is the impulse? Normally, the word impulse is designed to make us think of a sharp blow. So think of playing baseball, and the pitcher throws the ball, you swing the bat, and the momentum of the baseball, yeah, Haley? Haley, your hand raised. Is that an accident?
That was an accident, sorry.
Okay. Okay, so in baseball, the pitcher throws a baseball flying through the air. Its momentum doesn't change much, okay? But it changes a little because of gravity acting on it. But then you swing the bat, and when you hit the baseball with the bat, what happens is if we graph the force versus time, there's kind of no force for a while, and then the force goes up, it becomes big, and then it comes back down. Okay, so technically the impulse would be the area under this shape, which is kind of the same idea we had with work if the force didn't stay constant. But because we don't know how to find areas of weird shapes like that, what we in general do is we define a time, delta T, and we say that there's some kind of average force. We call it F average right here. That would be the force necessary so that the area of this red rectangle would be equal to the area of this green shape. So even though the real force is sort of curving and doing a weird thing, just because we're doing a introductory physics class, we instead think of this net force as an average force. How much force times how much time, this would be the average force times delta T. That would be the area of this red rectangle that I made. And so what we can do with this is we can use this to estimate the average force whenever we have a really fast, sharp blow, like a baseball hitting, a bat hitting a baseball, or a golf club hitting a golf ball. Those events are very short in time, So it's very hard for us to try to measure forces there. But what we can do is we can see how does the momentum of the baseball change, or the momentum of the golf ball change. How long is the contact? And that allows us to estimate this average force, or to compute an average force. So that's one potential use of this. We can find the average force for some kind of sharp event, like sharp. Another thing that's useful about this equation is just conceptually. It says that if we have a change in momentum, that change comes from two factors: the force acting on the object and how long the force acts. And so think about a car crash. Auto manufacturers actually, this is really the #1 equation that they're thinking about when they're thinking about auto safety, because they know at some point the car is going to crash. It's going to crash. And when it crashes, the momentum is going to change rapidly. Okay? And so what happens when the momentum changes? Imagine you're driving along and you crash into a tree or something. So you have all this momentum because the car has a big mass, a big velocity, and then it just comes to a screeching halt. Boom, it stops. So you're going to lose a lot of momentum. Now, how is that going to happen? That loss of momentum either happens from a very big force in a very short time, which is very bad for you. Okay, your body cannot handle big force for a short time, or the change in momentum happen with small force over big time. Now, obviously, we would prefer it if our body came to a stop in a big time with a small force. So auto manufacturers have basically created two key tools to allow this to happen. Does anyone know what car manufacturers do to increase the time so that the force can be reduced? What do car manufacturers do to make the car safer when you get into a crash? Ziad?
Airbags?
Yeah, airbags are #1. If you're in a 1950s car and you crash into a tree, that car just stops almost instantly, and you basically go flying through the steering wheel and get impaled. If you have a seatbelt on, then you stop very, very quickly. Maybe better for you if you fly through the window. But in a modern car, that instead of that collision lasting maybe 1/100th of a second, going from 60 to 0 a 100th of a second, it might take a 1/10th of a second or half a second. And if they can increase delta t by a factor of 10, then the force is reduced by a factor of 10. And that's why people commonly get into car crashes that basically destroy their cars, and they walk away, and they're not really hurt. The second thing the car manufacturers do is they build crumple zones into the front of the car. So when the car hits something, if it's over a certain speed when it hits, then part of the frame will crumple to take time. And by increasing the time, the force on the rest of the car and on you is reduced. And there's multiple crumple zones, so each one of those can take up some time. And that's really a brilliant idea by the car companies, because not only does it increase delta t, therefore reducing the force and making the car safer, but you also have to buy a new car. Whereas if you crash your 1950s car, the car might be fine, but you're dead. But you don't have to buy a new car either way. So, okay, so that's just a conceptual idea that there's this inverse relationship between the force and the time when we have a change in the momentum. So, okay, any questions about that? This is also, for those of you who are interested in medical things in the human body, this is also a real key component to why we have knees and elbows and joints the way we do. If you imagine like think when you're a kid and your ball goes over the fence and you jump over the fence, you have no fear of, getting hurt. You just jump over the fence. And when you land, your knees bend, and by bending, they're increasing delta T and reducing the force on your joints. And so you can actually fall from a pretty distance, and if you bend in the right way, your legs are natural shock absorbers. Okay, I know, if you play a sport that involves jumping really high, then when you land, your knees, they bend, and it's not that they're absorbing impact, they're really just increasing delta T and therefore reducing the amount of force. And if you don't believe me, just go find some stairs and just jump down one stair, but land with your knees locked instead of bent. And no, I'm kidding, don't do that, because you could hurt yourself, just from one stair. So it really, it makes a big difference. And our bodies are built with all of these natural shock absorbers that their sole purpose really is, well, no, I guess some of the purpose is mobility, but one purpose is to increase delta T and then reduce the force on, the rest of our body. Okay, but we're not going to work so much with impulse. So maybe next time we'll see a problem or two. But the key focus for us is going to be on situations where the change in momentum is zero. That is, there's no impulse or very, very small impulse. So let me give you an example of that, just so we can see how powerful momentum is. Just imagine we're in space, and we find this big, asteroid, and we want to drill into it and, find some good stuff inside. The estimates are that the asteroid belt has 80,000 times as many natural resources as the entire crust of the Earth. So as soon as Elon Musk or someone like him gets up to the asteroid belt and starts mining asteroids and getting, resources, and as soon as they can do that and use those resources to build more little robots to go out and mine more asteroids, then that person is going to own everything. So suppose you're out there and you see this asteroid, for some reason it's got some good stuff in it, but you have to drill in, you have to kind of crack it open to get to the good stuff. So you drill a hole, and in that hole you put a little explosive. Okay, you got a little stuff in there, and you blow the explosive. And so the explosive is going to blow, and when this happens, it's going to crack. And, one piece kind of goes that way, and the other piece goes this way. So suppose you do this, and it doesn't crack really symmetrically. So one piece, mass 2, has a lot more mass than mass 1. Maybe mass 2 is 10 to the 8 kilograms, but mass 1 is only 10 to the 7 kilograms. And mass 2, you see it moving off with a V2 equal to 15 meters per second. But you realize after you blow this thing and you look inside that all the good stuff was actually inside of M1. But you didn't stick with M1, you stuck with M2. And so you want to figure out, where did M1 go? And so to do that, you need to know how fast it's going. Okay, so the idea is we're in outer space. This thing's floating. There is no net force, external force. This explosion represents an internal force. So we can say that the change in momentum equals 0, which technically means P final minus P initial equals 0, or just P final equals P initial. But before we blow the explosive, the initial momentum of the system was just 0. I mean, at least in our reference frame, we're just floating above this thing. It's just hanging out there doing nothing. So the final momentum would be P1 final plus P2 final. keeping in mind these are vectors. And so the sum of because the initial momentum was 0, the final momentum is 0, and that means add up the final momentum of each piece. And what we get is P1 final is just minus P2 final. So that would be M1 V1 final equals minus M2 V2 final. Now this 15 meters per second, that's really the V2 final, and this V1 is really V1 final. That's what we're looking for. So V1 final would be minus M2 over M1 times V2 final. And that would be minus 10 to the 8 over 10 to the 7 times 15. That is negative 150 meters per second. So we can know almost instantly with very little work, very simple calculation. A very simple calculation tells us what this velocity of this piece is. And I want you to just compare that for a minute. Just imagine I gave you this problem on the contest coming up. We never had today's lecture. How would you do it? I mean, you know so little. You know the mass of each chunk and the speed of one piece, but you don't know what kind of explosive, you don't know how much energy is released in the explosive, you don't know how long the explosion takes, you don't know how fast the gases are moving. I mean, you know almost nothing. And yet conservation of momentum is enough for us to exactly determine what the final speed of this other piece must be. And I mean, it works. We could track that. And it also, furthermore, has to be exactly the opposite direction. Okay, so that is, if my V2 final is exactly on the x-axis, then V1 final must be on the negative x-axis. There's no room for it to go anywhere else other than the exact opposite direction. And its speed really is just determined by the ratio of these masses. So this is really very, very powerful, equation. There's a lot of information missing, and just like conservation of energy lets us skip entirely the process of finding the acceleration and computing the time and solving kinematic mass equations, this conservation of momentum lets us cut out a lot of middle steps. We do not have to talk at all about the forces involved in the explosion, nor how long they last, nor what kind of acceleration these masses get during the explosion, or any of that stuff. None of it. So it's very, very good. And it's also very, very accurate. I mean, we so far have not found any cases where momentum is not conserved. So it's also used in particle physics. Let me just give you an example. So in the decay of neutrons, beta decay of neutrons, which become a proton plus an electron. Okay, so neutrons occasionally will decompose, they decay, and turn into a proton and an electron. And when this happens, when this is observed, the proton is seen going one way, and the electron is seen going another way that's not opposite to the proton. So this was a big mystery, because if we look at this asteroid example, conservation of momentum should indicate that when one thing breaks into two, and one piece goes in one direction, the other piece has to go in exactly the opposite direction. And that's not what we saw with neutrons decomposing into protons and electrons. So it was positive. There must be a missing third piece. That's the only explanation. There must be a piece that goes that way, so that when I add up these three vectors, I can get, those are the final momentum vectors. I can add them up and get 0. And this missing piece was called a neutrino. Well, it turns out neutrinos are very, very hard to detect, which is why no one noticed them before this. But once, conservation of momentum is so reliable that anytime we see something where it looks like it's violated, we just have to look closer, and we will find that there's something we were missing. In this case, there was a new particle that was discovered because it looked like momentum was not conserved in this reaction. Okay, so any questions so far about momentum? All right, let's try a problem that involves a collision between two objects. So we already had this example where M1 was 100 kilograms and V1 initial was 5 meters per second. And then the second foot player comes along with V2 initial being minus 4 meters per second and M2 being 120 kilograms. And we said that player one wins, they stick together, they're going to move to the right, but how do we find what the final velocity would be? How fast are they moving to the right? Not very fast, because the values of momentum were pretty close. But to solve this, we just have to recognize that in a collision, collisions happen very rapidly. So the time interval is very small. And we can say approximately in collisions, P final equals P initial. That's for collisions in general. So the final momentum would be M1 V1 final plus M2 V final. And the initial momentum would be M1 V1 initial plus M2 V2 initial. Keeping in mind these guys are vectors, but we generally will have collisions in just one dimension. I'm not sure if that's exclusively true, but at least the vast majority of our problems will be in one dimension, meaning it's kind of like trains on a track. They can go forward or back, but they can't fall off of the track. Which means as far as vectors go, we really just have to worry about the signs. If we get a plus sign, it's moving to the right. If we get a minus sign, it's moving to the left. But we don't have to be finding components, using sines and cosines for the majority of our problems. Okay, so let's consider what we know. This is always a good thing to do if we know how to solve a problem. So what we know is mass 1 and mass 2. Those are given. And we need to know V1 initial and V2 initial. Okay, so we know everything on the initial side. And we're trying to make a prediction about the future. What will the final two velocities be? So at first glance, this should look like an impossible problem because it's one equation with two unknowns. But if the football players hold on to each other, if one of them, if the defensive tackle holds on to the running back, grabs on and pulls him down, then we could say V1 final equals V2 final. Or we could just call them both V final. If they're the same, we don't have to call them different things. So we can say this is really M1 V final plus M2 V final, or factoring out the V final, we have V final times M1 plus M2. And that's equal to M1 V1 initial plus M2 V2 initial. And I'm not going to keep writing vector signs over the top. We're just going to remember that velocity is a vector. So that is, we have to pay attention to the sign. We get M1 V1 initial plus M2 V2 initial. We're dividing both sides by M1 plus M2. And now we can plug in our numbers. So that's 100 times 5 plus 120 times negative 4 over 100 plus 120. And I get 0.091 meters per second. So this is very close to a tie because one had 480 units of momentum, the other had 500. Those were very, very close to each other. And now this is typical of a head-on collision. In a head-on collision, we're going to lose a lot of velocity, which means we lose a lot of kinetic energy, and both of these gentlemen are going to be really feeling this collision the next day, okay, unless their pads absorb a lot of the impact. Okay, any questions? Okay, let's just do an example of the same collision, but if it's kind of a rear end collision. So our V1 initial equals 5 meters per second, and V2 initial equals positive 4 meters per second. I'll just stick with the same masses. M1 equals 100 kilograms, and M2 equals 120 kilograms. So what if we have this collision? They're going to collide somewhere over in this vicinity, and they're going to stick together. What's the final velocity? So we would say same thing. P final equals P initial. P final would be M1V final plus M2 V final. Now that we recognize the final velocities are the same, let's just start out calling them that. Equals M1 V1 initial plus M2 V2 initial. V final, this is really the same as the last equal. The only difference is our numbers have changed, or really one number, the V2 initial. So our V final will be M1 V1 initial plus M2 V2 initial over M1 plus M2. Gives us 100 times 5 plus 20 times 4 over 100 plus 120. So we probably can expect that the first one is going to slow down a little bit, and the one in back is going to speed up a little bit. So the speed should be somewhere between 4 and 5. Kat.
Oh, sorry, I didn't mean to press that.
Okay. So it should be somewhere between 4 and 5. Because mass 2 is a little bigger, the final speed should be something a little closer to 4 than to 5. That's my prediction. So let's see what we have here. 500 plus 480 over 220. And that is 4.45 meters per second. Okay, so what we're going to see in this chapter is that collisions, which would be really impossible for us to have handled using other physics, because we don't know anything in detail about the forces going on in this crash. We don't know how long the collision lasts. We don't know how big the forces between them. There would be an action-reaction pair of forces. We don't know any of that stuff, but conservation of momentum allows us to just skip over that. And if the two objects actually stick together, then we can solve for that final velocity because we have really only one unknown. However, if we have two final velocities, if they do not stick together, which most collisions, most of the time if you have a car crash, the two cars do not stick together, well, then we don't have enough information, and conservation of momentum alone will not be enough for us to solve that. So let me show you kind of how it works. What this is, I'm going to lay out the strategies for solving different kinds of problems, but we won't solve these problems today. So for collisions, we're going to, normally we have P final equals P initial. And what this looks like is M1 V1 final plus M2 V2 final equals M1 V1 initial plus M2 V2 initial. All I'm doing here really is writing out the formula for momentum 4 times. Once for mass 1 final, once for mass 2 final, once for mass 1 initial, once for mass 2 initial. And as I said, generally we're going to know about the initial stuff and we're going to know the masses, but we are not going to know the final velocities, and that's what we want to figure out. So that's, that's, what's the word I'm looking for? That's tricky, okay? That's tricky because it's 2 equations with 2 unknowns, but it's not impossible. It just means we need to get more information. The problem is there's not one other piece of information that works for all problems. So what we have to do is we have to categorize the problems. So we split all collisions into 2 categories. One category is called elastic collisions, and the other is called inelastic collisions, meaning not elastic. So elastic collisions and collisions that are not elastic. So does anyone know what the word elastic means? Ziad.
Something that like you can stretch and it returns back to its normal shape.
That's right. If something can be deformed, but it returns to its normal shape. Now, so when I think of something that's elastic, I think of rubber. Rubber bands, you can stretch them, but they always return to their original shape. But it doesn't have to be rubber. A piece of steel could be elastic. If you drop a ball bearing or something, and it bounces on the ground, it still looks the same after it bounced. So it has returned to its initial shape. It didn't deform that much that we noticed, but if we watched it with super high-speed camera and it's a high-speed impact, we might actually see a steel ball deformed quite a bit. In fact, I'd like to see that if there's a video out like that. So elastic means something deforms, returns to its original shape. And in the context of collisions, what that means is kinetic energy final equals kinetic energy initial. It means kinetic energy is not lost. So I know the word elastic doesn't really sound like it means that exactly, so it may not be the best term. But think about something like a super ball. If you drop a super ball, really bouncy rubber ball, it has potential energy that turns into kinetic energy. It hits the ground, it smushes, it deforms, and then it springs back to its original shape, and it gets all of that kinetic energy back, and it goes back almost to the same height that it started from. So that the more elastic something is, the more after the collision it still has the energy if it didn't transfer that energy to something else. Whereas inelastic means, energy is not conserved. Ke final is not equal to Ke initial. Unfortunately, an inequality is not very helpful to us to solve problems. If I have 2 equations with 2 unknowns, and that's what ultimately we'll see we have here, then I can, in principle, solve that equation. But if I have 1 equation and then an inequality, it doesn't help me to know that they're not equal to each other because there's infinite possibilities of how they're not equal to each other. So we need to split inelastic collisions into two more subcategories. The first one is called totally inelastic. Totally inelastic. Let me rewrite that in a legible way. Totally inelastic. And the other is known as partially inelastic. So totally inelastic sounds like it means it loses all of its kinetic energy. If elastic means it preserves the kinetic energy, totally inelastic sounds like it means it loses all of its kinetic energy. Unfortunately, that is not what it means. It means it loses all of the kinetic energy that it could lose. If we take a look at this collision, let's see, this one, the rear end collision. There's no way that when these guys collide, they can wind up going less than the slowest one of them. The speed has to be, the one in front is going to slow down a little bit. The one in back is going to have to speed up. And if they stick together and the one in front speeds up, then the speed has to be greater than 4 meters per second. So there's no way these guys can lose 100% of their kinetic energy. But the idea, the reason for the name is that if we went to the right reference frame, then, so look at let me go back to these guys. If I were in a car, driving along, my car's drawings are getting worse and worse. If I'm driving along at 4.45 meters per second and I witness this collision, then these guys appear stopped. They appear to be stopped from that perspective, from that reference frame. So a totally inelastic collision is one that at least in one reference frame might appear to stop. It may appear to lose all of its kinetic energy. And the only way that happens is if V1 final equals V2 final. If they stick together, and that's what our first two examples were, they were examples of totally inelastic collisions, then it's easy to solve because V1 final and V2 final are just the same. Okay, so this is easy. That's why I started with it. Partially inelastic collisions are somewhere between hard and impossible. So we won't really do these. Okay, we won't really do any of those. Why are they between hard and impossible? Because what happens in a partially inelastic collision is we lose some kinetic energy, but they don't stick together. And just losing some energy, again, if we knew exactly how much energy, we lost 59% of the energy, then that would be something we could solve. But it's not very easy to access that information, to have access to that information. So for that reason, we generally don't see many of these problems. Or if we do, what happens is somebody just comes along and they tell us one of the final velocities. They tell us, V2 final was observed to be this. Now find V1 final. So if we're given one of the final velocities, then we can solve for the other. But in general, we can't solve these. So that brings us to elastic. Elastic are, they're hard, but doable. They're hard but doable. So how do they work? They work by, we say kinetic energy final, which would be 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared equals the initial kinetic energy, 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared. So if I look at those, I can see that they simplify a little bit in that the 1/2s cancel. And if I consider what's known, I still know all of the quantities on the right and the masses on the left, but we are still missing now the same two unknowns. So this becomes now a 2 equations and 2 unknowns situation. We can solve it, but it's hard. Any questions so far? Okay, does anyone know how we would solve these 2 equations? How would we solve them? Assuming we had numbers for everything but V1 final and V2 final. Well, I mean, you know, if I offered it for extra credit, you would give it a shot. And probably what you would do is you would take one of these equations and solve for one variable and then substitute. Just like you would if you had x plus y equals 6 and x minus y equals x minus 2y equals 3. You would solve for x, potentially plug it into the other equation and solve that for y. So that's how we could solve this. But it turns out to be extremely hard to do so. So I'm going to teach you a trick how to solve this. It's about the hour mark, so I normally like to take a break at this time. I don't have too much more lecturing left, maybe about 10 minutes. So part of me says maybe we should just finish it and then be done with today's lecture. The other part says you guys are probably already glazing over and maybe need a quick break. So raise your hand if you feel like you'd like just a short break. Raise your hand if you just want to get this over with. You didn't have to be so aggressive with the hand raising, you know. Okay, let's just get it over with. I'm going to make a new page so that we can see what this trick looks like. So we have 2 equations. We have P final equals P initial, and KE final equals KE initial. And we already have written these down. Let me just kind of copy and paste them to save time. So where did it go? I'm going to take this one. Stop. Okay. And then the other one. Okay, and I'm going to clean it up a little bit. Get rid of those 1/2s, all these little underlines. And so we have M2 V2 final, let's see, 1 V1 initial. Just make sure everything is transferred. Okay, good. Now, if we look at these equations side by side, we see that they are almost identical. The only difference is the squared term. And that squared term is why we don't want to do substitution. Because if we solved, let's say, this left equation for V1 final, and we got, you know, this plus this minus this all over M1, we get this big ugly for V1 final. We substitute it here and we square it. We wind up getting like the worst, nastiest looking FOIL, you know, from math class you've ever seen. And it becomes very, very hard quadratic equation to solve. So we do not want to do that. Instead, what we're going to do, the trick is we're going to use them to derive the equation. What I'm going to do is I'm going to take everything with M1 and move it to the left, and everything with M2 and move it to the right on each equation. Okay, now this trick, you're not going to do this trick. when you're solving problems. This trick is so we can develop a new equation, and that new equation is very simple. And then we will use that simple equation to solve our problems. Okay? So this trick, you don't have to memorize this trick or be able to reproduce it. But what do we get? We get M1 V1 final minus M1 V1 initial equals M2 V2 initial minus M2 V2 final. And on the other, the other equation, we're going to get M1 V1 final squared minus M1 V1 initial squared equals M2 V2 initial squared minus M2 V2 final squared. So it's a little tedious to do this, but the end of it is going to give us a very nice, easy, simple equation. So we can factor out now M1 on the left and M2 on the right, and that's the reason why we're moving things around. And over on the right, we do the same thing. We factor out the M1 and the M2. Okay, now we look at them again, and they still look very similar. Again, the difference are the squares. But the fact that we have differences of squares, in math class, you may recall, if you have a squared minus b squared, you can factor that into a minus b times a plus b. Raise your hand if you kind of vaguely remember that from math class. Okay, good. So we're just going to use that. This gives me M1 times V1 final minus V1 initial times V1 final plus V1 initial equals M2 times V2 initial minus V2 final times V2 initial plus V2 final. Really running out of room there. We just move it a little bit. Okay. So now what we're going to do is we're just going to compare. I don't want to rotate that. I want to just move it down. Okay, we're going to compare these guys side by side. Just look at the two equations for a minute, stare at them, and look at it until you see something. Raise your hand when you see something. Anybody something? Okay, one person sees something. Keep looking. Anything comparing the equation on the left and the equation on the right. There's something very kind of special happening here, and I want to make sure that we see it. Okay. A few other people are seeing something. Good, good. Cody, what are you seeing?
There's kind of a bit of a pattern.
Okay.
So the mass one and the velocity of the first mass are on one side, and the second one is on the other side on both equations.
So you're saying basically this stuff that I underlined in red appears in both equations?
Yep, yep. But it's kind of, yeah.
And then also this, right?
Yep.
Okay, exactly. That's exactly what I'm looking for. So what I underline in red appears, the whole left-hand side of this equation appears as a piece of the left-hand side on the other equation. The whole right-hand side of the first equation appears as a piece. Now the left-hand equation says that the green line and the red line are equal to each other. So that means if they're equal to each other, I can just cancel them out. And what we're left with is a very simple equation. This equation is only true if the energy and momentum are conserved. And so when we want to solve an elastic equation, instead of using, I want to do that in a different color. So instead of using these two equations, we don't want to use those two equations because the second equation has squares. It's too complicated. So we will use our two equations, these two, the ones I've outlined in red. Now they both have the same variables. It's kind of customary to rearrange this second equation and put everything that has to do with final back on the left. So that looks like B1 final minus B2 final equals B2 initial minus B1 initial. And it's even customary to make it so mass 1 always comes first. So we have B1 final minus B2 final equals a minus sign times V1 initial minus V2 initial. So what I did here is I factored out a minus sign. Factor out a minus 1. But if you multiply through by minus 1, you would get back to this. So this is actually the form we will see this equation in on our equation sheet. And the reason for this form is because there's an interpretation. This is called the relative velocity final. Okay, relative velocity means the difference between the velocities. I'm going to show you that in the context of our football players. So the relative velocity, V1 initial minus V2 initial would be 5 minus 4. That would be 1 meter per second. That is how fast they look like they're going to each other. Or if we look at the example where they're doing head-on, the relative velocity is 5 minus a negative 4. That would be 9. So these guys each see the other one is coming at them at 9 meters per second. That's called the relative velocity initially. Okay, and what this equation says is that the final relative velocity is equal to minus the relative velocity initially. And that's just that's a convenient thing to remember. Okay, if the difference in the speeds is 1 meter per second before the collision, the difference has to still be 1 meter per second after the collision. So I want to give you one quick example how we would use these equations to solve. And we're going to use the same two M1, and M2. For football players, but now maybe these are not football players, they are bubble soccer players. Has anyone ever seen bubble soccer? Okay, good. I want to play bubble soccer. I have never done that, but so bubble soccer, you're wearing a great big bubble suit and you bounce off of each other. So they are going to bounce off of each other. And I want to find, if this is V1 initial and V2 initial, what are V2 final and V1 final equal to? So we start with the conservation of momentum. M1, V1 final, plus M2, V2 final equals M1, V1 initial plus M2, V2 initial. And I'm really just trying to make an illustration here, so I'm going to use the numbers. We have 100 V1 final plus 120 V2 final equals 100 times 5 plus 120 times 4 times minus 4. And that is just 20 on the right-hand side. So 100 V1 final plus 120 V2 final equals 20. If we divide both sides by 20, we get 5 V1 final plus 4 V2 final equals 1. So there is my first equation with two unknowns. It's now looking very similar to math class because I'm just trying to do an illustration here. Now we take that second equation, not the conservation of kinetic energy, but this conservation of relative velocity. V1 initial minus V2 initial equals negative V1 final minus V2 final. So that is 5 minus a negative 4 equals minus V1 final plus V2 final. So I'm distributing the minus sign through this equation. So the first piece gets a negative sign, and the second one, two negatives make a positive sign. So now we can take this and solve it for, let's say, V2 final. 9 plus V1 final equals V2 final. Once I solve for that, I can substitute. So we have 5 V1 final plus 4 times the quantity 9 plus V1 final equals 1. That's going to be 9 V1 final plus 36 equals 1, or 9 V1 final equals minus 35, and V1 final will be negative 35 over 9. So that is minus, let's round it to 3.9 meters per second. And when we're solving two equations with two unknowns, once we solve for one, we always take that and plug it back in to our substitution equation. We get 9 plus a negative 3.9 equals V2 final. That just gives me V2 final equals 5.1 meters per second. So what happens in this bubble soccer match is this one that's moving at 5 bounces back at a speed of minus 3.9. The one that's moving minus 4, it's going to bounce forward at a speed of 5.1. Now, the difference between these two is still 9 meters per second. The difference is the one that was moving in the positive direction now moves in the negative direction, and the one that was moving in the negative direction now moves in the positive direction. That's basically the reason for the minus sign in this equation. All right, so that is an example of how we will solve elastic collisions. Any questions? All right, I appreciate it. You guys, that was probably our longest lecture so far, so thank you for sticking with it. Even if you did it only to end the misery sooner, I'm just kidding. I know that this is probably a highlight of your day. And if you have questions about homework or other things, then stick around. And if you do not have any questions, then now send me an email and you can ask those later. Thanks.